Okay. So now we know what the eigenvectors and eigenvalues are. They are some mathematical object that can be defined on and square matrices. Also, we also have discussed we also discussed the matrix invariant. So what are these matrix invariant? So matrix invariant is a thing so that gives you the same result for similar matrices. Okay, so that means for two seemingly completely different matrices may refer to the same linear transformation, depending on the choice of basis. So the question is, well, for any given matrix A, for any given square matrix A, or for any given linear transformation, then maybe we can choose a very nice basis so that its linear, so that its matrix representation is very nice. So, okay. So I'm kind of getting a little bit abstract, but what is the nicest matrix that you can ever imagine? Well, what is the easiest matrix? What are the easiest matrices? I believe they are the diagonal matrix. Diagonal matrix is the easiest matrix to deal with, right? So the idea is this: given any linear transformations, maybe I can try to find a very nice choice of basis so that its matrix representation is a diagonal matrix. Is that possible? How can I do this? How can I get such a nice basis for that linear transformation? That is today's main topic. So it goes like this. Yeah. I have a linear transformation and I want to find a very nice basis B of this vector space Rn so that its matrix representation, this is the matrix representation of this linear transformation with respect to this basis, so that this matrix is a diagonal matrix. So in other words, for given a matrix A, and we want to find a non-singular matrix M such that M inverse times A times M is, well, this is lambda. This is the capital letter lambda, and this symbol is especially preserved for the diagonal matrix in our context. So we want to find a very nice non-singular matrix M, so that under the similarity transformation, I want to transform A into a diagonal matrix. And today we'll try to find such a nice matrix M. The matrix A is given, and we want to find such a nice matrix M. Okay, so how can I make such a nice non-singular matrix M? The idea lies in the eigenvectors and eigenvalues. So, and this is the idea. Let us assume that xi is an eigenvector of an eigenvalue lambda I. So in other words, and this is very wild assumption, but let us try to assume this. I can suppose that I can find a basis of the vector space Rn that entirely consists of the eigenvectors. So, well, this is n-dimensional vector space, right? So it means I could find n linearly independent eigenvectors. So that means A times xi is lambda 1 times x1. So A times x2 is lambda 2 times x2, all the way to A times xn is lambda n times xn. So, and x1 to xn, they are all linearly independent. So we are assuming that such a linear independence. Well, there may be some repeating eigenvalues. So lambda 1 so I have n eigenvalues from lambda 1 to lambda n, but there can be two same eigenvalues, but we are only assuming the linear independence of the eigenvectors. Okay, there could be a repeating eigenvalues. So. Okay, so now we are assuming we have such an n distinct linearly independent eigenvectors from x1 to xn. Now I want to make a matrix M whose columns are precisely these eigenvectors. Okay. So this is an n by n matrix. Now I want to multiply the matrix A by this matrix M, and since the columns of the matrix M were the eigenvectors, so the resulting matrix, the columns of the resulting matrix is clearly has to be A times x1 to A times xn, right? Okay. Now, since they are the eigenvectors of the matrix A, so A times xi could be lambda 1 x1, lambda 2 x2, and lambda n xn. Okay. All right. Now this is an interesting part. So I can transform this guy as I can write down this guy as the matrix M times this diagonal matrix. Why? Because this is lambda 1 and all the other guys equals to 0. So this guy times this guy 0 times this, and this 0 times that, 0 times that. And sum of all such a matrix, sum of all such vectors now goes to the first column. So this one must be x1 times lambda 1, and this guy should be, the second column has to be x2 times lambda 2, and Okay, Now I realize that this matrix is precisely the same as this guy. So, we have A times M is M times lambda. In other words, and since we are assuming that they are linearly independent vectors, so M is a non-singular matrix, which has an inverse. So multiplying this inverse matrix of A, so inverse of M to the both sides of this equation, I have this. Okay. So in this case, we can conclude that under this similarity transformation, matrix A has been transformed into another diagonal matrix lambda. So whenever this is possible, we say that the matrix A has been diagonalized. So A has been diagonalized. So this is the diagonalization of the matrix. Okay. Okay. So So that means so therefore, whenever we can find a basis consisting of entirely eigenvectors, then we can actually diagonalize the matrix. So let me turn to this example. Let me try to diagonalize this guy. So actually, this is an example that we did in our previous lecture. Just try to compute the characteristic polynomial of this guy. Then we did that before, and whose eigenvalues were -1 and 2, and from the tedious computation, we can conclude that the x1, which is 1 and 1, was turned out to be the eigenvector of this eigenvalue -1 and x. Oh, sorry, I messed up. So this is x2. This is the eigenvector of this eigenvalue. Okay, and for me, it looks like these two eigenvectors are clearly linearly independent. So I am safe to say they form a basis of R2. Okay, then so I have a basis consisting of eigenvectors. So one, this is the first eigenvector, and 5, 2, this is the second eigenvector. And this guy inverse times matrix A times this now. Can you guess the entries? Can you guess the entries of this resulting matrix? This guy must be what? -1. This guy has to be 2, and all the other entries should be 0. -1, 0, 0, and 2. If you can't trust me, then why don't you use any calculator? So you can go to any linear algebra calculator, and you can try to take an inverse of the matrix, and you multiply these two matrices all together. Then you can easily convince yourself that it has to be the answer is this diagonal matrix. Okay. So so in this case, diagonal so I can say for this matrix, the diagonalization was possible. So now I guess at this point now we can all agree that diagonalization is very nice because it makes a very nice matrix representation of the linear transformation. But the question is the diagonalization always possible? So in other words, can I always find a basis that consisting of the eigenvectors? Can I always find such a nice basis? The answer is no, not always possible. Then when such a nice diagonalization is possible, so that those two questions are going to be the two most important questions in today's lecture. So we will try to answer that one by one. So, and the first very important theorem is suppose xi is a non-zero eigenvector of an eigenvalue lambda I. So the index I is varying from 1 and 2. So I have 2 eigenvalues and I have 2 eigenvectors associated to these eigenvalues. If these eigenvalues are different, then x1 and x2, they have to be linearly independent. So this is very important theorem because in order to do a diagonalization, then we have to find a linearly independent eigenvectors, right? And this theorem says if 2 eigenvectors belongs to 2 distinct eigenvalues, then these 2 eigenvectors are automatically linearly independent. Okay. So, so maybe, but this is huge maybe, but maybe I can try to state like this. Suppose that I have a matrix that has n distinct eigenvalues. Okay, so their eigenvalues are all different. Then in that case, their eigenvectors are going to be automatically linearly independent. Am I right? Therefore, that matrix must be, I can diagonalize the matrix. Okay. All right. So let me prove this. Let me prove this. Suppose. Okay. So I am supposed to prove that the linear independence of x1 and x2. So I should begin from this equation, this vector equation. And under this assumption, I should prove that C1 and C2 must be 0. Okay. Maybe I want to multiply the matrix A to the both sides of this equation. Then this is C1 A x1 plus C2 A x2, which equals to 0. But since x1 and x2, they were assumed to be the eigenvectors. So these two should be C1 lambda 1 x1 plus C2 lambda 2 and x2. Okay. Okay, so I have two equations, C1 x1 C plus C2 x1 0, and C1 lambda 1 x1 plus C2 lambda 2 x2 equals to 0. I have two such equations. So what? I want to multiply the both sides of this by lambda 1 and subtract it from this equation. So in other words, I want to do this. C1 lambda 1 x1 plus C2 lambda 2 x2 0 minus C1 lambda 1 x1 plus C2, not lambda 2, but lambda 1 x2 0. I obtained this second equality by multiplying both sides with this by lambda 1. And by taking subtraction, this guy minus this guy 0. And C2 lambda 2 minus lambda 1 and x2 equals to 0. Okay, now this condition must kick in. So lambda 2 minus lambda 1 is clearly a non-zero number. And this is also non-zero vector. Therefore, in order this guy to be 0, the only possible option for me is C2 has to be 0. So C2 equals to 0. Therefore, C2 equals to 0 implies C1 also must be 0. Okay. So x1 and x2, they are linearly independent. Okay. So there is very nice corollary of this theorem. If a matrix has n distinct eigenvalues, then A is diagonalizable. So therefore, since we had two distinct eigenvalues, and therefore this guy should be diagonalizable. Okay. Good. So therefore, the question, okay, so whenever you have a matrix that has n distinct eigenvalues, then you're always good to assume that that matrix is diagonalizable matrix. The question is, the question is, what happens if your matrix has some repeating eigenvalues? Like such as, suppose that your matrix is 3 by 3 matrix, and the root of the characteristic polynomial has one double root and one distinct root. In that case, you have a repeating eigenvalues. In that case, you cannot guarantee the linear independence of the eigenvectors. So, in order to deal with such cases, now we have to define somehow some tricky notions. Not tricky, but okay. They are not tricky, but they are some easy notions. But anyway, you have to understand the meaning of the algebraic multiplicity and geometric multiplicities. So, okay, let me try to explain this. I have an eigenvalue. So lambda 0 is an eigenvalue of A n by a matrix A. And I want to define, and for any eigenvalues, we can define two multiplicities. The one is the algebraic multiplicity, and the other one is the geometric multiplicity. So I will begin from the algebraic multiplicity. If k is a maximal integer such that lambda minus lambda 0 to the k divides the characteristic polynomial of A, then k is called the algebraic multiplicity of lambda 0. Wow. That sounds very tricky, but it's not a big deal. So what is this? So, well, once you find, you can always find the characteristic polynomial of the matrix. Then once you factorize the characteristic polynomial into linear factors, then there can be some repeating factors, right? Then in that case, well, then suppose that this guy consists of 2 factors of lambda minus 1 and this times 3 factors of lambda minus 3. In that case, that means A is the 5 by 5 matrix, and I have 2 eigenvalues, 1 and 3. Okay. Then in that case, the algebraic multiplicity of 1 is just 2, and algebraic multiplicity of the eigenvalue 3 is 3, right? So, well, it's not a big deal. So factorize this, and you can see the powers of the root of each of powers of this characteristic polynomial, and that power is the algebraic multiplicity. Okay, easy. Okay, good. So what about the geometric multiplicity? I define some very tricky space E of lambda 0. So what is this? This is a collection of all vectors such that A times X equals to lambda 0 times X. So in other words, this is a collection of eigenvectors of eigenvalue lambda 0. Okay, well, but this time around, well, our convention usually avoided including 0 as the eigenvector, but in this case, 0 should be included in this space. Well, and this guy is called the eigenspace of the lambda 0. This is eigenspace. And I claim this eigenspace is a subspace of Rn. Right? Right? So if you, because just try to, well, whenever you have the eigenvector of the lambda 0, and any linear combination of these eigenvectors should be another linear eigenvector of the same eigenvalue lambda 0. So this is a clearly subspace of vector subspace. Okay. And any subspace, we can define the dimension of the dimension. And the geometric multiplicity of the lambda 0 is nothing but the dimension of the eigenspace of the lambda 0. Okay. So okay, so these are the algebraic and geometric multiplicity of any given eigenvalue. So they are both of them, they are 2 integers. Okay. These are two algebraic multiplicity and geometric multiplicity. They cannot be zero, right? Algebraic multiplicity cannot be zero, right? If algebraic multiplicity is zero, then that means that number is not a eigenvalue, so that doesn't make any sense. And also, geometric multiplicity should be always also has to be greater than equals to 1, right? Because you should be able to find at least one non-zero eigenvector for any eigenvalue. So they are both integers from 1 to greater than 1. And these integers cannot be greater than n, right? You know, algebraic multiplicity cannot be greater than n, right? Because why? Because this guy has the degree n polynomial. Same is true. The eigenspace is a subspace contained in Rn. Therefore, the geometric multiplicity cannot exceed n. Okay, so they are just some numbers, integers, between 1 to n. Okay. Okay. I will be introducing many different definitions in today's lecture. So I will try not to hesitate and explain each of these definitions by using these examples. I have this matrix. This is 3 by 3 matrix, and find all eigenvalues of A and find the geometric and algebraic and geometric multiplicity of each eigenvalue of A. Okay. All right. So the first thing I want to do is I want to find the characteristic polynomial of the matrix A, which is the determinant of A minus lambda I. This is 2 minus lambda 2 minus lambda 2 and 2 minus lambda. And this is a triangular matrix, so its determinant is easy to compute, which is just nothing but 2 minus lambda to the third. Sorry, I changed my mind. I'll just say minus lambda minus 2 to the third. And so in this case, I have only one eigenvalue, which is 2. And what is algebraic multiplicity? Very easy. Just read this number, read the exponent. That's it. So 3 must be the algebraic multiplicity of this guy. Okay. And its algebraic multiplicity is 3. Okay. All right. Okay. So what is the geometric multiplicity? Let me try to find the geometric multiplicity. So A minus, 2 times I x equals to 0. That is 0, 2, 2, 0, 0, 2, and 0, 0, and 0. Not great. X1, X2, X3. So I have X1 plus, not X1, X2 plus X3 equals to 0. and x3 equals to 0. So I get two equations. So what do you have? So x3 equals to 0 implies x2 also has to be 0. So x2, x3, they are both zeros. Therefore, the eigenvector is just x1 and 0, 0. So, and eigenvector. So, what do you think is the dimension of the eigenvalue 2? So, what do you think is the dimension of the eigenspace of eigenvalue 2? It's just 1. Why? Because we were only able to find only one single linearly independent vector contained in this eigenspace. Okay. So this eigenspace is just simply span of 1, 0, 0. Therefore, its geometric multiplicity is 1. Okay, so algebraic multiplicity was 3 and geometric multiplicity was 1. At this point, I would greatly enjoy if I can find some relation between the algebraic and geometric multiplicities. So, and actually there is a relation. The geometric multiplicity is always less than or equals to the algebraic multiplicity. So, in other words, geometric multiplicity cannot exceed the algebraic multiplicity. Which can be summarized as, which can be stated by this theorem. For any eigenvalue lambda, algebraic multiplicity is always greater than or equals to geometric multiplicity. So this equality actually forces us, sets us the upper bound of the number of the linearly independent eigenbases. Okay. So, well, let me just go back to the beginning. So we were at the very beginning of today's lecture. So we wanted to find the n linearly independent bases consisting of eigenvectors, right? And the number of linearly independent eigenvector is clearly related to the geometric multiplicity. And the number of such linearly independent eigenvectors for any eigenvalue cannot exceed the algebraic multiplicity. Okay, so let me prove this. But before I try to prove the theorem, so I will need to prove another a small lemma, which is this. Let me prove the lemma first, because this lemma is usually translated in Korean 보조정리. So 보조정리 means that to prove the big theorem, so you will need some small tiny little statement, and lemma is that tiny little statement. And what is that? What is a block matrix? Block matrix is X is an n by n matrix, and it consists of, in this case, 4 blocks. Well, this is K and this is K. So A, which is on the top left corner of the matrix X. This is a K by K square matrix contained inside this large n by n matrix. And this is K, this side is n minus K. So this is K by n minus K narrow matrix. And this is n minus by k wide matrix, and this is k by k square matrix. So, well, I can, so each of these small matrices, I would say they are the block matrix. So for any n by n matrix, you can always divide the matrix into blocks. But in this case, I'm assuming even more. Suppose that this block, this bottom left corner block, solely consisting of the zero entries. So that is a zero matrix. So suppose that I have such a weird matrix X. Then the determinant of this large matrix X is, this is a k by k matrix. This is a square matrix. Therefore, I can define, so there is a determinant of A. And this is also n minus k by n minus k square matrix. So determinant of this guy is also defined. And therefore, and it says the determinant of this is the determinant of this times determinant of that. Determinant of these two matrices. Provided that enough time and effort, and maybe with some additional additional cup of coffee, but I guess you can easily prove, you all can easily prove this lemma. But for my own purpose sake, so let me prove this. Let me prove this. Okay. Induction on K. So the size of matrix X is fixed. This is always n by n, but I will do the induction on the size of this K. Okay. So suppose that K equals to 1. So this is a n minus 1 by n minus matrix, and this A is just a 1 by 1, just a number, and this guy is a 0. Or this is a all zeros, and determinant of X, to find the determinant of X, I will try a cofactor expansion along the first column, this column. Then this guy times the plus minus sign times the determinant of C, and plus this guy times the cofactor of this, and this guy times cofactor of that. But these are all zeros, so they can be all ignored. So therefore, this is just simply A times plus minus factor times determinant of C. But since this is a 1 by 1 entry, so this guy is just 1. So this A times determinant of C. But this can be also considered as determinant of A times determinant of C. So good. So the base case is good. Now for the induction step, now I have, suppose the induction hypothesis holds for the integer k. Now I will need to test my hypothesis when my number is k plus 1. So this k plus 1, this n minus k plus 1, this is again k plus 1 and n minus k plus 1. What now? So, well, again, I am applying the cofactor expansion along the first column. Then this guy times the cofactor of this guy, which is this. And cofactor of this guy, which is the determinant of this huge matrix. But because of the induction hypothesis, the determinant of this huge matrix can be written as determinant of A11 times determinant of C. Okay. Same is true for this entry. This guy plus minus determinant of the cofactor of this should have a factor. Oh, well, this guy times it. But again, by induction hypothesis, so this one should be written like this. So or it should be written like that. And I can see a common factor, which is determinant of C. So determinant of C is now factorized. And combining this is clearly the cofactor expansion of this k plus 1 by k plus 1 matrix A. Okay, so this is determinant of A. The proof is done. Okay. Okay, great. Okay, now what? Okay, so I will prove the theorem. Oh, sorry. Okay, so this is the proof of the theorem. I have the matrix A, and the matrix A has an eigenvalue, which is lambda 0. And let us suppose the dimension of this eigenspace is K. Okay. So in other words, I am assuming that geometric multiplicity of this guy is K. And the dimension of this guy equals to K means that I can find K linearly independent vectors from this subspace. And because of the definition, they are not merely linearly independent vectors. They are the eigenvectors, right? Eigenvectors and linearly independent. So therefore, A times each of these vectors, xi, is lambda 0 times xi. Okay. Okay, good. We found, and these are K linearly independent vectors. So, but they are not they may not be the sorry, they may not be the basis for the entire vector space Rn. So since this is n-dimensional space, so let me try to find n minus k additional linearly independent vectors so that collection of all these vectors form the basis of this guy. So maybe you can try to find these guys from the orthogonal complement of this space, but whatever. So you can always find you can always find these vectors so that this guy is the basis of this whole space. Then I will try to build a matrix consisting of whose columns are these vectors, like this. And since we are assuming they are bases, so they are linearly independent columns, therefore, M is a non-singular matrix. In other words, M has an inverse. This also is an n by n matrix. Now, what I want to do is this. I want to multiply A by this matrix M. Okay, and so A times this guy. And because the same logic, the columns of the resulting matrix has these looking columns from A1 to AXK and AY1 to AY n minus K. They must be the columns of this resulting matrix. Okay. Okay. Well, I really don't care about these guys. But these guys, the first K columns are, since they are the eigenvectors, so they are just lambda 0 x1 lambda 0 times xk. Okay. Now, this guy can be written like this. So the first K columns can be written as lambda 0 times x1 plus lambda 0 times this guy, 0 times that guy, 0 times that guy. So therefore, if I factorize this guy, this by that, then the first column of this matrix must be the lambda 0 and 0, 0, 0. And the second column of this guy is also going to be 0, lambda 0, and 0, 0, 0. And so therefore, the first K columns of this matrix must be the diagonal matrix whose diagonals consisting of the lambda zeros. Okay. And for these guys, so this is AY1, but AY1 is some, and for this column, I am actually trying to express this guy as a linear combinations of x1 to yn minus k. But they can be some numbers. I really don't care about that. So I'll just put a bunch of stars over there. Okay. And okay, now what? So, and this is M. Yeah, this is M. So it turns out M inverse AM is this matrix. And clearly, the matrix on the right is a block matrix, right? This is a k by k square matrix, and this is n minus by n minus square matrix. And these are some other numbers, and this is clearly 0. Okay. And the characteristic polynomial is independent under the similarity transformation. I mean, two similar matrices share the same characteristic polynomial. You remember this? So I'm going to name this guy B. Is the characteristic polynomial of B. And I'm going to call this guy, this bottom right corner, the bottom right block C is lambda 0 minus lambda raised to the power of k times characteristic polynomial of C. Okay. But at the same time, this one should be called as characteristic polynomial of A. So lambda minus lambda to the 0, lambda 0 to the k. As a polynomial, this polynomial divides the characteristic polynomial of A. So what do you know from here? K is less than equals to the algebraic multiplicity of lambda. Okay. Great. Okay. And actually, I did this before. So I will just make it quick. Geometric multiplicity of any eigenvalue is greater than or equals to 1. Okay, which is very obvious. So if lambda 0 is an eigenvalue of A, which implies that its characteristic polynomial, when lambda is replaced by lambda 0, should be 0. That means A minus lambda 0 times I is a singular matrix. That means it has the null space of that matrix must contain at least one non-zero vector. So that non-zero vector is a member of the eigenspace. Therefore, the geometric multiplicity is always greater than or equals to 1. So I can say the geometric multiplicity can have value. He is always greater than or equals to 1 and less than or equals to the algebraic multiplicity of that eigenvalue. Okay, good. Great. So let me summarize what I have explained so far. For given n by n matrix A, and A is diagonalizable if and only if A has n linearly independent eigenvectors. if A has k distinct eigenvalues from lambda 1 to lambda k, then some of these, for some of the algebraic multiplicity of all these eigenvalues must be, always must be n. Right? Because the why? Because the characteristic polynomial of matrix A is n. And they are just lambda minus lambda I, they are just factors of linear factors of the characteristic polynomial. Therefore, sum of all these algebraic multiplicities must be precisely always have to be must be n. Okay. But on the other hand, the sum of geometric multiplicity of these eigenvalues can be less than n. So in other words, A is diagonalizable if and only if the algebraic multiplicity agrees to the geometric multiplicity for every single eigenvalue of A. Okay. In that case, A can be diagonalizable. Okay, so what we know so far is diagonalization is very nice, very nice, but the diagonalization is not always possible. Actually, diagonalization is, well, almost always impossible because all these eigenvalues, all these different distinct eigenvalues must satisfy this equality. In such extreme case, that A can be diagonalized. A can be diagonalized. All right. So enough. Okay. This is all. But this is okay. So much for the theory. And now let me turn to some concrete examples. Let me try to diagonalize this. So I will compute the determinant. Determinant is 2 minus lambda 0, 0, 1, 2 minus lambda 1, minus 1, 0, and 1 minus lambda. So this is 2 minus lambda by cofactor expansion. And this is so 2 minus lambda squared times 1 minus lambda. So this is the characteristic polynomial. So I have two distinct eigenvalues. Oops, sorry. I have two distinct eigenvalues, 2 and 1. So the case number 1, eigenvalue 1. In this case, its algebraic multiplicity is 1, and geometric multiplicity is always greater than 1, and in this case, it has to be less than the algebraic multiplicity. So in this case, algebraic multiplicity and geometric multiplicity of this guy, this eigenvalue, they are the same. Okay. But anyway, let me find this. Since lambda is 1, so I want to compute 1, 0, 0, 1, 1, 1, minus 1, 0, and 0. Everything times x1, x2, x3. So I have x1 equals to 0 and x1 plus x2 plus x3 equals to 0. So I have these two equations. So the vector x is this guy is 0, and this is minus x3 and x3. So I will just say the eigenvector x1 is 0, minus 1, and 1. Okay, that was a easy part. Now let me go to the hard part. So the second eigenvalue was 2. And so this is 2, plugging 2 here, 2, 0, 0, 0. So I get this equation. And turns out I have only one single equation, x1 plus x3, 0. Okay. So in this case, this is x1 and x2, they must be opposite. So minus x3 and x3 and x2. Okay. In this case, I have two free variables, x2 and x3. So I should be saying x2 is just 0, 1, 0. And x3 is minus 1, 0, and 1. So these two guys are the eigenvectors of eigenvalue 2. Okay. Now, can you guess the geometric multiplicity of each of these eigenvalues? So what is the geometric multiplicity of this guy? 1. And since I can find 2 linear independent vectors for this eigenspace, so geometric multiplicity of this guy was 2. So both of these eigenvalues, they are satisfying the not inequality, but they are satisfying the equality. The algebraic and geometric multiplicity of these two eigenvalues, they are all turned out to be the same. So in this case, this matrix is diagonalizable matrix. Okay, right? So I'll put my x1, x2, and x3, which is, what is my x1? 0, minus 1, 1, 0, 1, 0, and minus 1, 0, 1. Then this matrix inverse times original matrix A times M is the resulting matrix must be the diagonal matrix. And what is the first entry? 1. And the second and third entry must be 2 and 2. Okay. Do you think you can do this by yourself? This is not horribly complicated computation. Just keep track of all these eigenvectors and make them as the columns of matrix M, and you invert it, time multiply by A and multiply by N, then I'm pretty sure that you will get the diagonal matrix. Okay. I mean, as a matter of fact, I really want to put more emphasis on the actual computation, even more than the theory. Yeah, theory is very important. Yeah, I'm not saying theory is not that important. Theory is important, but what really matters, what is the purpose of learning the linear algebra? Learning linear algebra just makes you, so you are learning linear algebra just to compute something. So the actual computation is very important. So whenever you see the exercise, you do not take them for granted. You just try and solve it one by one and try to make every possible mistake you can. Then after that, you are learning some linear algebra. Okay. The next example is I want to try to diagonalize this matrix whose diagonal entries are 2, 2, and 4. So in this case, the characteristic polynomial is very easy to compute. So determinant a minus lambda times I is 2 minus lambda, 4, 6, and 2 minus lambda, and 4 minus lambda. So 2 minus lambda squared and 4 minus lambda. So I have two eigenvalues, 2 and 4. And its algebraic multiplicity is 1, and its algebraic multiplicity is 2. If lambda is 4, then I am supposed to solve, this is 2, so 4. So I have to subtract every single diagonal entry by 4. So it's minus, minus, and okay. X1, X2, X3 equals to 0. So minus 2x1 plus 4x2 plus 6x3, 0, and minus 2x2 plus 2x3 equals to 0. And yeah, I have these two. Yeah, this requires some computation. So x2 is x3 from the last equation. So x1 and x2, they were the same. So 10, so x1 must be 5, I guess. X1 must be 5 times x2. So x is x1, x2, x3 is 5 times x2 and x2 and x2. So x1 is 5, 1, 1. Okay, so this is my eigenvector. The second eigenvalue was 2, whose algebraic multiplicity was 2. Okay, so in this case, I want to subtract every single diagonal entries by 2. So 4x2 plus 6x3, 0, and 2x3, 0. Since x3 equals to 0, x3 equals to 0, so therefore x2 must be 0. So x2 and x3, they are all zeros. So this is just x1 and 0 and 0. So I should be saying 2. One and 0 and 0. Okay. Okay. So what can I say about the geometric multiplicity of this eigenvalue? The algebraic multiplicity and geometric multiplicity, they do not agree. Actually, in fact, the geometric multiplicity is 1, which is strictly less than the algebraic multiplicity. So is it diagonalizable or not non-diagonalizable? This is a non-diagonalizable matrix. Okay, great. Not diagonalizable. Okay. Great. Before I move on, so before I move on, so I really want to take a little time to explain what happens if you have a complex eigenvalues. So because I'm intentionally avoiding the complex eigenvalue case, but well, they are not that hard. So let's take a look at this. So this is a matrix whose characteristic polynomial is, well, irreducible degree 2 quadratic polynomial. So which is so lambda is plus minus I, and when lambda is I, then it has this one, and lambda is minus I, and whose eigenvalue is this. So well, even though they are all complex, they are all complexive, but well, there is nothing to worry about. It's just same thing. You can still define the algebraic and geometric multiplicities. So for each of these two matrix eigenvalues, their algebraic multiplicities are all ones, and their geometric multiplicities are all ones. So therefore, it should be diagonalizable. So in fact, so this is my x1 and this is x2. So x1 goes to the first and x2 goes to the second column. And you invert it, multiply the original matrix K, and times this one on again, then you're going to get the diagonal matrix. But this time, your diagonal entries are the complex numbers. But they are just the same. Okay. All right. So what if your matrix has a complex eigenvalues? So I know many of you are not huge fan of complex numbers. Why? Because, well, whenever you're doing some experiment or any kind of, whenever you experiment, especially you're scientists or engineers, then your experiment only yields you some real valued result. So I guess that is why many people don't like working with complex numbers. But complex numbers is not a big deal. And suppose that you have a square matrix with real entries. And suppose that you were able to find a complex eigenvalue lambda. And because of the Euler's formula, every complex number can be written as a magnitude times cosine say theta plus I sine theta, like this. And suppose this value is a eigenvalue of the matrix A, and this x is an eigenvector of lambda. And here I intentionally divided x into these two terms, because every number can be written as a real part and imaginary part. I'm doing the same thing. So x is an eigenvalue of the lambda. So a times x has to be lambda times x. But now what I want to do is I want to put the complex conjugate to the both sides of this equation. You know what complex conjugate is? Okay, yeah. So taking the complex conjugate, so I put a little bars over there, but complex conjugate can be always broken down, always respect the multiplication, but so because we are assuming that A is a square matrix with real entries, so for real numbers, complex conjugate can do anything. So A times x bar is lambda bar times x bar. Okay. So what do you know here? If lambda is an eigenvalue, then lambda bar is also the eigenvalue of the same matrix A. And in that case, you can automatically get the eigenvector of this guy, which is x bar. Okay. Okay. So, well, maybe if you're good with working with complex numbers, then maybe this is probably the end of the theorem. If this is the course, and if I were greater, then maybe I will give you the 100 point for this. But if you really want to translate everything in real numbers, real world, then I recommend you to do this. So I have two eigenvalues, lambda and lambda bar, and eigenvectors x and x bar. And I want to apply A times x plus x bar. And x plus x bar is what? Since this is x bar must be A minus IB. So x bar so this one should be 2 times A. A is here. Then, but because of this one also must be lambda x plus lambda bar times x bar. Okay. And so this is lambda times x plus lambda bar times x bar. Okay. And you just try to simplify this and combine the like terms. It turns out 2 times e to the r times cosine A minus sine B. And similarly, this time I will try A, not x plus x bar, but A times x minus x bar. And because of similar computation, it turns out A times B is e to the r times sine A plus cosine B, cosine theta times B. So let me summarize this result. So if I just get rid of these two factors from here and there, I will get this result, and I will get that result. So what do you know here? So having a complex number as your eigenvalue means this is working like this. So if the eigenvector of the eigenvalue lambda was A times B, so if my this is A and this is B, A and B they are real vectors, right? So, and what is this? If you take a close look of these three relations, then A times A is rotating by degree theta, theta radians, and stretched by the factor of e to the r. And B is this guy, also rotating by theta radians and stretched by the factor of e to the r. This is, this is not precisely rotation. Why? Because in order to be truly a rotation, then A and B must be orthogonal, but there is no guarantee that A and B are orthogonal vectors. So I cannot say these are indeed truly a rotation, but some sort of rotation. You can try to convince yourself this is more like a rotation, but not exactly rotation. Okay. So this is for today, and see you next time.